You carry more computing power in your pocket today than an entire building could hold 75 years ago. Back then, machines like the ENIAC filled massive rooms and failed constantly. These early systems relied entirely on vacuum tubes. They were bulky, fragile glass bulbs that generated intense heat. Engineers spent hours every single day hunting down and replacing the burnt-out units just to keep the machines calculating. By 1948, researchers at Bell Labs recognized a physical wall. If computing was ever going to scale up in power, the physical hardware had to scale down. They needed a solid-state alternative to fragile glass and hot filaments. The solution they developed was the bipolar junction transistor. It looks rough in its original prototype form, but this small piece of germanium eliminated the need for a vacuum tube. The mechanical problem it solved was difficult: how to use a tiny electrical input signal to dictate the flow of a much larger electrical current, all without relying on any moving physical parts. Think of it like a water faucet. Instead of turning a mechanical handle to release a heavy flow of water, this device uses invisible physics to open the valve. Controlling heavy power with a faint electrical signal allowed machines to shrink to the microscopic level. To understand how that invisible valve operates, we can look at a standard component you will find in almost any modern electronics kit, the common TO92 package BJT. If you split it open, you won't find tiny wires or filaments inside. Instead, there is a solid block of silicon separated into 3 distinct horizontal layers. These layers are manufactured through a process called doping, where impurities are added to the silicon to change how it conducts electricity. The 2 outer layers are N-type, meaning they hold extra electrons. The middle layer is P-type, meaning it has an absence of electrons, empty spaces that we simply call holes. Each of these 3 layers connects directly to an external middle pin. The bottom layer is the emitter, the middle layer is the base, and the large top layer is the collector. Notice that the internal structure is highly asymmetrical. The emitter is thick and heavily loaded with extra electrons, while the middle base layer is microscopically thin and very lightly doped. By arranging the silicon in this specific, uneven geometry, the device ensures that charge carriers are never simply passing through. It forces the material itself to act as a regulator, where a tiny input determines the movement of a much larger supply. When no voltage is applied to the middle base layer, the device sits in the cutoff state. At the borders where the N and P layers meet, natural barriers form. These act like solid walls, preventing any electrons from moving from the emitter up to the collector. The action starts when a small positive voltage is applied to the base pin. This creates a forward bias. The positive charge pulls on the barrier separating the emitter and the base, causing that barrier to collapse. With the wall gone, the heavily concentrated electrons in the emitter have an open path. Because the transistor uses both negative electrons and positive holes to function, we call it a bipolar device. The swarm of electrons shoots forward into the P-type base layer. You might expect those electrons to turn and flow right out of the base pin, but because that middle layer is incredibly thin, the electrons move so fast that almost all of them overshoot the exit. They are instantly swept up by the strong electric pull of the large collector region above. This chart shows the mathematical relationship of the device. For every single electron that manages to exit through the tiny base, hundreds more rush past it into the collector. A tiny sliver of input base current accurately triggers a towering amount of collector current. By utilizing those invisible boundary layers to trap and then release a swarm of charges, this device acts as a current-controlled valve. It takes a microscopic signal and physically scales it up into a massive output of power. Let's zoom back out from the atomic silicon layers and look at how this component operates on a printed circuit board today. The most straightforward application is switching. By completely cutting off or maxing out that base current, you create a digital switch that turns heavy circuits on and off thousands of times a second without any mechanical wear. Its second strength is amplification. If you feed a weak, fluctuating signal into the base, like a faint audio signal from a microphone, that pattern is perfectly mirrored by the heavy collector current. The shape of the wave stays identical, but the volume is drastically increased. Now, if you open a modern smartphone, the central processor relies primarily on a different component called a MOSFET. Those are preferred for dense microchips because they consume less power at a microscopic scale. Yet, the 70-year-old BJT remains relevant. Because it can handle substantial amounts of current without failing, it is still the preferred component for power management systems, motor drivers, and high-fidelity audio amplifiers. The BJT was the first device to prove that solid crystals could do the work of a vacuum tube. By moving from fragile glass to reliable silicon, it provided the technical blueprint for the integrated circuits that allowed computers to shrink from the size of a massive room to the palm of a hand.